Let's have a look at these buoyancy questions here. For each one of these scenarios, they want you to compare the mass of the object and the fluid displaced, and they'll want to compare the volume of the object and the fluid displaced, and the densities of the object and the fluid displaced. So we'll start here with object 1. It's floating on top. I've drawn to make it clearer the water line right here. So what do we know about their masses? Well, let's first do a little free body diagram. Anything that is floating, we know that there is a buoyant force up, and we know that there is a force of gravity down, and because it's just resting there, those two must equal each other. So let's start with that. We know that the force of gravity must be equal to the buoyant force. And let's substitute in for these. The force of gravity will be the mass of object 1 times gravity, and the buoyant force will be the weight of the fluid displaced. So in other words, the mass of the water displaced times gravity. And we can see here that gravity will cancel on each side, so the two masses must be equal to each other. And that is true always if something is floating. So if something is floating, its mass must be equal to the mass of the fluid pushed out of the way. Or you could also say its weight is equal to the weight of the fluid pushed out of the way. Anytime something's floating, so always remember that. So let's do, that's just the very first part for mass, but what about volumes here? Well, we can see that the volume of the water pushed out of the way, which is just this area, is less than the volume of the object. Some of the objects peeking above the water here. So the volume of 1 is greater than the volume of the water. And then that leaves us with densities. So I think we have an intuitive sense, and we're right that this thing's less dense than water, but let's see why that must be the case. Remember, density is mass over volume. They each have the same mass, but the object has a bigger volume. And therefore, when you divide by a bigger number, it will make it less. So the density of object 1 is less than the density of the water there. What if it is floating like this, just floating right in the middle of the beaker there? Well, the same thing we said before is still true. If it's just staying there, the buoyant force must be equal to the force of gravity. So just like we said before, if their forces that are equal to each other and the buoyant force is equal to the weight of the water, then the mass of object 2 must be equal to the mass of the water pushed out of the way there. What about their volumes? Well, this thing is submerged. So the volume of that object is equal to the volume of the water pushed out of the way. And so then finally, what about their densities? Well, if they have the same mass and they're being divided by the same volumes, then they must have the same densities. So the density of object 2 is equal to the density of water. And that's the only way something will just float right there in the middle of a container of liquid. So looking now at object 3. So for object 3, it has sunk. That means that while it was sinking, that the force of gravity on it must have been bigger than the buoyant force, and that is why it sunk. Now we also have a normal force to help balance out the gravity. But while it was sinking, the force of gravity was bigger than the buoyant force, and that's still true right now. So that lets us know when we go to set up our equations from before that the force of gravity on 3 was greater than the weight of the water. And so because we're going to have mass times gravity again, and the gravity is going to cancel out, that means the mass of object 3 is greater than the mass of the water that it pushed out of the way there. It's submerged, and so whenever something is submerged, their volumes are equal. So the volume of object 3 is equal to the volume of the water that it pushed out of the way. And so then finally, we'll put these all together. Remember, density is mass over volume. Since the object had a big mass over an equal volume, so this will be a bigger number overall. Sorry, there should be a greater than sign there. And so the density of object 3 is greater than the density of water. All right, flipping on to the back side there, they say we take object 2, and object 2 was the one that just floated right in the middle, if you remember, and we put it in some oil, and they tell us that this oil is less dense than water. So the density of the oil is less than the density of water. What will happen to our little object that floated right there in the middle? Well, if we reduce our fluid's density, then we reduce our buoyant force. Because remember, buoyant force is the density of the fluid times the volume of the fluid displaced times gravity. So less dense fluid means less buoyant force. And so our object from number 2 that was floating right in the middle will have less of a buoyant force, and it will sink to the bottom. They also ask us 3 questions about generalizing the rules on the front, and we basically already answered this. How can something float right in the middle? If the density of the object is equal to the density of the fluid, then it will float right in the middle. Why does something sink? If the density of the object is greater than the density of the fluid, as in this case, then the object will sink. And how does something float? If the density of the object is less than the density of the fluid, then the object will float there. Next part is they give us a ball here, and they say we've got this ball of some material, its mass m, and it floats, and if you look there, it's floating just about like halfway in, halfway out. What if we get another ball made of the same material, so same density we'll assume, and it's a bigger one, its mass is 2m. What will happen when we stick it in here? Well, as best as I can draw it, about half in, half out, that's supposed to be, it will be the same. It's not the masses that matter, it's the density that is important there. So when this thing is in, it's still half the density of water. So it only still needs to push out half of its own volume before that weight of water is equal to its own weight. And so it will begin to float when it is half in there. So it says in its final position, how does the buoyant force on the larger sphere compare to its weight? Well, it's going to float, so the buoyant force is going to be equal to its own weight, in other words. How does the volume displaced by the larger sphere compare to that by the smaller sphere? Well, obviously, it's pushing out way more volume there because it has to equal its greater weight in order to float. So it says, are your answers to this one and this one consistent with Archimedes' principle? Yes, because we've been using Archimedes' principle in order to solve this. Archimedes' principle, remember, says that the buoyant force is equal to the weight of the fluid, I'll put, pushed out of the way there.